that thing. All right, good evening everyone. A little bit of pre-meeting arrangement, and I'm having to work around a very large furry object. I'll see if I get a look at the video for you. There you go. So Nico, say hi to everybody. Everybody say hi to Nico. He is the one who usually interrupts our lessons, and this is his standard mode of interruption, which is to sit on the desk that I paid for this desk, but you think it's yours, and interfere. Okay, is that where you're going to sit? That'll actually work. So if you stay there, this is going to be just fine. So try to stay there. So yes, I'm aware I'm talking to a cat as if it's an adult and it can understand me. I have a niece that she claims that our pets can understand us after living with us for a few years, and we should just talk to them like they're ordinary people. And she does it with her pets and her kids, which are distinguishable only that her kids are humans. Otherwise, they behave like wild animals, and it seems to work. All right, so I'll get started now. The topic for today is entitled Introduction to SWM, and we'll introduce the SWM software, and I hope to get as far as at least getting an initial build of the Goodwin Street example. In this morning's version of this class, I wasn't able to get that far, but I had some other network and recording issues. There's the usual collection of readings. This one you've seen before, as is this one, and this one. So those four are just repeats from our last lesson. And then there's a couple of links to localized copy of the SWM5 User's Manual, the Applications Manual, and a Quality Assurance Report if you actually are concerned about the underlying computation engine. I just selected the Applications Manual, and the reason I did that is this is kind of an IQ test. I really don't know what EPA's thoughts at the time were, but the manual itself contains a self-extracting archive, so if you need to use it, you're going to need to read through the first few sections carefully, and at some point it explains how you can extract the files. I think this zip file, judging by the date and time, is because of its size, it's probably not the self-extracting archive. The user manual itself is right here, and we're well past version 5. I think we're at 5.2.2 or 5.2.3. And as we're going through this, I just want to call your attention to the first part of the user manual, past the marketing section. It has a description on how to install it. If you're familiar with the Windows operating system sequence, this is kind of elderly, but it's still installed just fine in Windows 10. And then they have a description of how one goes about building and using the software. And although we won't follow this exactly, we're going to be quite close to it. If you have an input model, you also can create direct input files. The next section is what they call a quick start tutorial. And the only humorous part from my perspective on quick start tutorial is it's not very quick and it's not a very good tutorial. So I will try to do a different variant of tutorial description of the software, and if none of what I say makes sense, go ahead and consult the user manual and give this one a try. So on to the lesson notes. Actually, back for a second. In the data links section, There's supplemental data, and it contains a Goodwin Street Storm Sewer BMP, which is what we use as the base map, and some links to some other swim related stuff. I'm going to see if the links are even, oh, they are still working. Cool. Let's see, this should go to a GitHub site. Maybe. It does. So if you really get into this kind of software, there's various working repositories here. And NSIM is a national center that's working alongside with this Open Water Analytics and EPA to move the SWM software forward quite a bit. So those are resources you can visit at your leisure. Let's move on to the actual notes. So it is downloading the PowerPoint, and there we go. And we shall begin. We push the chat box off to the side a little bit. So this is entitled Lesson 18, Introduction to SWM, and this is fall of 2020. And the forward button does not work. Let's try it again. Maybe again. Maybe again. So SWM, the acronym, stands for Stormwater Management Model. It was originally created by a group of graduate students and professors at the University of Florida in the early 1970s. And the first 4 versions of SWM were written in Fortran, probably Fortran 5, then ANSI 77 Fortran, and then by version 4 they were probably up to Fortran 90. In the 1980s to the early 2000s, in the early 2000s, around 2008, it was refactored into C++. So refactor is the computer programmer jargon for take the Fortran code and rewrite it in C++. And the timing was most likely coincident with the F2C compiler becoming released, which means Fortran to C. So that made parts of the refactoring manageable. Also, around that time, the Windows operating system had achieved enough capacity that graphical user interfaces were realistic considerations in government-built and distributed software. So version 5 has a graphical user interface associated with it. Just as way of understanding it, the graphical user interface part of SWM and the computation engine are actually 2 separate pieces. When we run it today, we'll be running it from the GUI. The GUI invokes the computation engine. We don't perceive that. But there's 2 parts, and that was a brilliant decision on their part because it allows the GUIs to evolve over time without breaking the underlying computation engine. And why that's important is that computation engine is quite mature. Some of the commercial products that use the SWM computation engine essentially as is are Mike Urban, which is a commercial software product out of, I think that's out of DHI, which is used to be the Dutch Hydraulics Institute, but they're just a company now. And then Sobek is from the Delft group, also in the Netherlands, which uses the SWM computation engine. XP SWM, which at least kept enough of the name so that you could recognize it, is an Australian company that provides an extended performance SWM. That's what the XP means. And it has a very good user interface. And then Civil Storm, which is either a Bentley or Hasted Methods or whoever owns them today product, is also an interface on top of the underlying SWM computation engine. So these 4 commercial products is just a sampling. There's more. What they bring to a practicing engineering firm is computer interfaces that integrate SWMM with other design tools that a engineer is likely to use. So for instance, SOBEC, XP-SWMM, CivilStorm, MikeUrban, they have the ability to invoke a SWMM run directly from a geographic information system, assuming all the packages are bought and paid for. So that's their real value. The key is that the actual hydraulics and hydrology calculations are the same regardless of which of those products you use or the company that you end up working for uses, and you can expect the commercial ones to change over time. So it started its life as a simplified hydraulic model, not much different than the rational method approach that we used in our last lesson to create an initial storm sewer design. Over the years, it evolved into a fairly elaborate hydraulics model, so from simplified to elaborate, and it picked up some hydrology capabilities along the way. So as of today, it's arguably an integrated hydraulics model, and more integrated than, say, HEC-HMS and HEC-RAS, which are 2 separate modeling suites that combined together can be used to do integrated hydraulics calculations. It's pretty useful in urban settings, and one could look at the history and conclude that that's really what SWMM was designed for. It can be used in non-urban settings, and it can be used for everything you would use HEC-RAS for in a FEMA study, and it's accepted by FEMA. SWMM models are for various activities, but unless you start out your modeling career in SWMM, it's unlikely that once you've developed a skill set with HEC-RAS that you'd actually want to switch, because they work fundamentally differently, and the input and data management is quite a bit different. They're more or less somewhat incompatible with one another, although a good computer hack can make SWMM talk to HEC-RAS and vice versa. It's used today pretty much for drainage modeling, for best management practice performance estimation. So a BMP, or best management practice, I think the modern terminology is called green infrastructure. These are widgets, devices that are engineered into a drainage network to provide certain water quality enhancement or control features. And then LID performance is yet another acronym. LID means low impact design. It's also a unit of measure for a particular volume of unregistered narcotics, but that's a different story, for lid performance estimation. And LID, BMP, GI is the kind of buzzwords du jour in the environmental aspects related to stormwater management. And there's actually a pretty healthy industry in that. So if you find any of this interesting, you got a good 40-year career ahead of you in coming up with acronyms and doing engineering design that a good engineer would do anyway. But if you can put that BMP stamp on it, you can charge your client a premium. And that was not a cynical statement, that's simply business. So to acquire a copy of SWMM, there's a couple of ways. You can Google EPA SWMM, get to the EPA website to find the software, and then download the self-extracting archive, and I suggest you download the user manual. If you're a Windows person, you're good to go at that point. If you are hampered by being in the world of Macintoshness, such as I am, this won't work for you unless you have a hypervisor software, such as Parallels or VMware. For us, those are actually the best alternatives because they're not terribly expensive, and you can be up and running pretty quickly. The other alternative would be to use use the online one in this class. That's what it's there for. Or I just recently posted a YouTube video on how to get EPANet to run on Amazon Web Services in the free tier, and I don't have that for SWM. So I'm intentionally leaving the PowerPoint temporarily to return to the server. I really should wear my glasses when I do this. And go to the toolkit to, that's not where I wanted to go. Go to the software selection and show you where there's some copies of SWM. So we go to software and we want to go to Windows builds, and let's see if I've updated this or not. So I have 5.1.013. The current version is 5.2. So if we go to the EPA site, it brings us to SWM. Oh, so 5.015. That's weird. I thought we were at 5.2. Well, okay, so I'm wrong. 5.015. So this self-extracting installation and this one are different. So the one at EPANet is more current. The upshot of that difference will be relatively trivial as far as today's lesson is concerned, because the 015 corrects some bugs that were in the earlier codes and incorporates more BMP and LID features, which we're not really going to get much into in this class. So that's an alternative. If you happen to be running a Macintosh and your operating system is Mojave or Mojave, you could go to this location and download the SWM Unwind information, but it explicitly shows as of this July it does not work on Catalina or newer. The last working operating system was Mojave. So one of these days I'm going to take this down because it has ceased to be useful. And I will levy my usual complaints against the world of software industry. We have one other option for SWM, which is our friends SWM in a Box, which we will go to later on in the lesson. So returning to the presentation, what we will do when we turn the thing on is we'll take a brief tour of the interface. The interface will look an awful lot like EPANet. The reason for that is the interface is actually written by the same dude, and like all good creators of things, if you got it to work once, you reuse as much as you can, because reinventing the wheel is not a very productive use of one's time. So like EPANet, SWM drainage networks are constructed out of nodes and links. The special kind of node that every SWM file, SWM model has to have is called an outfall node. So it, to some extent, plays the same importance as a fixed grade node did in EPANet. Although, unlike EPANet, the fixed grade node was a source of water. In SWM, the outfall is the sink of water. It's where everything drains to. Additionally, we have objects called subcatchments and rain gauges. And a rain gauge is just a conceptual thing. The icon for it's a little cloud looking, so I call it Puffy the Cloud. And so we can program Puffy the Cloud to produce a particular hyetograph. And then the subcatchments are drainage areas that we define that will convert rain coming from Puffy the Cloud and turn it into runoff. And then that runoff is directed to the nodes and conveyed from through the links to the outfall. a little bit more serious is that we actually have to make date and time specifications, because SWM is by default a dynamic model, and it actually doesn't do a steady flow explicitly. There's a trick to making that happen that we'll employ. And we have hydraulics and hydrology specifications that are independently defined, although they're connected in a simulation. So a little bit more attention to input than we experience with EPANet. So let's learn all about nodes. In the program, there are two types of nodes. There are junction nodes and storage nodes. The fundamental difference between the two, other than their name, is how they behave in the case where the computed water surface elevation goes above the top of the node. Generally, we supply the invert elevations, which is the elevation of the bottom of the node, and it makes those computations relative to that elevation. So again, the emphasis on elevation mapping is not wasted when we're doing drainage engineering. So an ordinary junction node is a node that connects hydraulic elements, and hydraulic elements are generally links. The other element that a junction node can interface with is a subbasin. The junction attributes themselves are the invert elevation, which is the elevation of the bottom of the node, the max depth, or actually the max elevation but entered as depth, which is the elevation of the top of the node, and there's a couple of tricks we can employ. First is to set the maximum elevation equal to the land surface elevation, and what that will give us is when the program plots the profile, the program joins the maximum elevations in any profile plot, and if we've set those so that they're at the land surface, we actually can see where the land surface is in the drawing, and then we can see where the water is relative to the land surface, and generally that's important to us in drainage engineering. The other trick that I've employed is set it to the land surface plus some additional depth. So perhaps make the max elevation equal to the land surface plus 3 feet. And what that allows is it allows the program to actually store water on the land surface, and we can produce a dual drainage network and see where the water is both on the surface and in the underground portion, and that's very useful in engineering design and assessment. When we run the program, it computes the depth of water at the node that's required to satisfy the continuity equation as well as the head loss equation for that moment in time. But there's no storage provided, so the node essentially has zero area. So if that continuity and head loss requirement drives the computed water surface elevation above the land surface elevation, the program detects that as flooding and declares that water lost. And by lost, it just gets accumulated in some variable somewhere. And so if we have flooding losses in the output report, we've run a simulation for a case where our drainage system isn't working as designed. And that's actually desirable for us, because we can use that to locate where that flooding occurs and then implement design changes, retest our design in the model until we can contain the design discharges completely in our planned drainage network. So here is a illustration of a junction and some pipes taken from an older SWM report. And so here we have one pipe, which is pipe N. This pipe is N minus 1, and judging from the drawn slope, the red arrow indicates the direction that the designer expects water to flow. And here we have pipe N plus 1. And the red arrow is indicating its direction of flow. So in this junction J, there's at least 3 links depicted in here. There's link N minus 1, link N, and link N plus 1. The bottom of the junction is called the invert elevation, or the junction elevation. Pipe N is entering the junction at the invert elevation. So this pipe would have what's called a 0 offset either at its entrance or exit end. Pipe N minus 1 is entering a distance above the invert elevation, and so that's called a pipe offset. And because of the way the pipe is drawn, that's going to be an outlet offset, because this pipe is outfalling into the junction. So there's an outlet offset, whatever this distance is that I've circled in red. Pipe N plus 1, which is leaving the junction, again from the slope, this becomes an inlet. It has an inlet offset, shown right there as that distance. And in the junction itself, it's shown here having some finite area, although in the computer model it has no area unless we provide for flooding. And when we run our program, it's going to compute our water surface elevation. So let's suppose it computes an elevation right here. And so that's as if this whole junction is full of water. This pipe is going to be full of water, this pipe will be full of water, and this pipe will be full of water. So the 3 pipes will be surcharged, and we'll get a report that we have surcharged pipes in the simulation. But the water surface elevation of the junction is below the ground surface. So that's generally desirable. Alternatively, if the program computes the water surface elevation up here, this portion is considered to be flooded, and whatever volume of water is associated with that is removed from the simulation, duly recorded, and then thrown away. So if we run a simulation and we get the water up here, if our goal was to keep the street surface dry, we will have failed. So that's the main utility of one utility of the program. However, an ordinary junction node often is not useful, because we know that in real systems we have the ability to store a little bit of water right here, which is above our junction max depth, and we want that water to be stored there when it gets too deep, and then have the ability to return back into the junction. And so we'll see how to do that in a second. So these 2 diagrams depict the case. On the left, all the pipes are full. They're surcharged, in fact. On the right, all the pipes are full and also surcharged. In the left picture, the node is not flooded, and if it was an ordinary node, nothing special goes on. The computations continue. In the right picture, the node is flooded, the pipes are surcharged, and whatever excess would be required to leave the node is removed entirely. So if it's an ordinary node, the way the picture is drawn isn't actually reflected in the program. It doesn't actually have that storage at the top unless we turn on the flooded node attributes. If we do provide for flooding, we will provide a maximum surcharge depth above the top of the node, and the ponded area that the node stores water in. And internally what the program is doing is it's treating the node as a vertical wall storage tank. And so the ponded depth plus the max depth would be the total depth at the node if flooding is occurring and we've turned on the flooding feature. Let me get the draw thing working right, and let's do magenta because I just love saying that name. So the ponded depth plus the max depth, which is the height to the top of the node, these are combined in this calculation, and so that's the computed water depth of the node, and then whatever this area is multiplied by that depth is the volume in storage. And so as the hydraulic system drains, this water over time will drain back into the system and make its way out to the outfall. So let's now look at the software itself. We're going to do two really simple problems at first, and then we'll try to load in the Goodwin Street case that we left off with last time. First we're going to do a rectangular channel, and then we'll do flow in a sewer. So let me exit here, and yeah, that's what I did earlier. So we kind of want to keep my problem statement here, and I actually have already built this example earlier today, so I can sort of cheat, which will be good because then we'll be able to get to the Goodwin Street example. So we'll go to swim in a box. Let me go ahead and grab the credentials, hit copy, fire that up, hit that, hit paste, and fingers crossed. Sweet. Okay, that's what it's supposed to look like. And in this case, this is laid out very much like the EPANet shared one was, except it's SWM instead of EPANet. There is a directory called SWM projects, and we're going to want to use, we're going to do SWM 2 and 3 today. SWM 2, I believe, is lesson 18 example 1. So I'm not going to necessarily do that. I'll go ahead and launch SWM. So I double click on the launchy thing. And this is running SWM version 5.014, which is in between the current EPA one and the one that was stored on my server. And so I'm going to see if it remembers example 1. It does. So in the interest of not having to draw 19 dots again, I will just go ahead and load in what I did this morning. What's on the screen in front of you is the interface, and if you look at it, it looks an awful lot like EPANet. Not exactly, but an awful lot like it. Has the same kind of menu structure at the top, the little picture menu, so if you're working at McDonald's you can have a cheeseburger or the hamburger, and then a choice of objects to build our model with. In this one we have junctions and conduits, so that's no different than EPANet. We have storage nodes, which looks kind of the same as a reservoir picture because that's what the the programmer used. And then we have some other things that are different. We've got a pump, we've seen that before. So the upside down triangle is called an outfall node, and this guy here is Puffy the Cloud, and that is a subcatchment element. So this diagram depicts a rectangular channel starting in an outfall and working its way upstream all the way to the inflow. So the reason it has this bend in it, it looks like it's folded on itself, is not a consequence of that's how it actually looks on the Earth, but to be able to fit everything into the drawing space. Because unless we turn on the georeferencing part, all this is a connection relationship drawing, or an influence diagram. So for example, so I'm doing this on purpose. If I redraw it like that, I've actually made no changes to the underlying hydraulic model. And we can use the profile tool to convince ourselves of that. So I'll start at node 20, end at outfall 1. I'll let the program traverse the path, press OK, and that is the profile. Ignore the blue stuff for the time being. I haven't explained that yet. So we see that we're on a constant slope, and we're roughly 4,000 feet of channel is depicted in this diagram. Now if I move this junction and attempt to refresh the profile, nothing changes because nothing has changed. So all the information is actually contained in the underlying database. So for example, this upstream most junction has invert elevation of 3.8 meters. In this case we're in cubic meters per second flow units, so distances are in meters. The name of the junction is 20, and it has an inflow associated with it, and we can look at the value of the inflow as 2. So here we have 2.5 cubic meters per second, so let's change it to agree with the example. Press OK, and we would then move, if we were first building the model, we'd then move from node to node to set the elevations. So junction 19 is at elevation 3.6 meters. Junction 18, 3.4 meters, so we're losing 0.2 meters every junction, and from this diagram these are 200 meters apart, and we can verify that by just picking one of the lengths. Indeed, they're 200 length units long, in this case our meters. The roughness is 0.025, which is given in the problem statement. It's a rectangular open channel, and it's set to have a bottom width of 1 meter. It has sidewall heights of 2.2 meters. That was most likely selected to guarantee that the water stays in the channel for the example. And lastly, when we get down to the outfall, let's take a look at the problem statement. Let's do that again. Let's do that again. So we have steady flow over a weir, and so we're declaring this location the outfall, and we're actually going to specify the flow depth as 2 meters, and that's done by declaring it as a fixed stage boundary condition, and we're setting the stage at 2 meters. In the options section is where we actually prepare most of the simulation information. So we have three kinds of routing models. We could choose steady flow, kinematic wave, or dynamic wave. I'm choosing dynamic wave, which is the closest to the gradually varied flow equation, and when we hit a equilibrium condition, it will be gradually varied flow. The infiltration model doesn't matter. We're allowing ponding, and it defaults to do a 6-hour simulation, and unless you tell it otherwise, it thinks it's today. For this first time, we'll just accept the default time steps, but it's going to report every 15 minutes, but it's actually going to make calculations on 5-minute time steps. So let's go ahead and change that. And I think you can just type it in directly, but I don't want to do 3. I want to do every 5 minutes. Very good. And then in the dynamic routing, we have a choice on the inertia terms to keep them, to ignore them, or dampen them. Earlier today, I dampened them. I think for this evening, we'll ignore them and see what happens. We have 2 surcharge methods. We're going to be using the X-Tran method. The other one is to treat all the conduits as having things called Priestman slots. They accomplish the same goal, but they work quite a bit differently. And for much of drainage engineering work, the X-Tran method probably is a better choice. We'll leave all the other stuff as defaults, press the OK button. And now let's go ahead and run the simulation, and we do it by clicking on the lightning bolt. And this is good. Our run was successful. We have a minor continuity error, which we should get. So if you get a 0% here, or if you get like a 3000%, that means something's wrong. But anything between those two is great. Let's go back and look at our profile, because now we've done the computations, and look at that and go, that's a terrible profile. Keep in mind that our downstream end, our flow depth is 2 meters, so it seems to have that right. And there's water up here, which makes sense because we're putting in 2.5 cubic meters per second. But we know in our hearts that the 2 waters should connect. And that's because this is a simulation model. We're 5 minutes into simulation, so the channel started as miraculously dry, and by doing that we actually have to let the computer program fill it up. So all these calculations right now are just spin up. And we get down to here, and that's our 6-hour simulation. And if we look carefully at the upstream end, it kind of looks like the water is at the top of the channel, or possibly even higher. So we can't tell that in the picture. But if we choose the report and pull up the status report, we'll scroll down through this. And we have that line right there, flooding loss. And so what that is indicating to us is a portion of the total inflow is having to be wasted through flooding, which means that the computed water surface elevation would prefer to be outside of the channel. So there's not enough capacity. So while we have this up and running, we'll do a little bit of what if, and then we'll move on to the next example. So we're experiencing just a wee bit of network lag. I think the easiest is going to for me to reduce the inflow. So that 2.2 meter deep channel can't sustain 2.5 cubic meters per second of flow, but let's see if it can handle 2. Now let's do 1.9 just so that we're not deceiving ourselves. Let's say we have some way to reduce the flow into the system to 1.9 cubic meters per second. We now can ask ourselves, is the system going to be able to accommodate that flow rate? There was that zero flow error, which normally would be disturbing, but let's see what we get when we that's hardly, I don't think that even refreshed. I know that didn't refresh. So we'll refresh it manually. And you'll find if you are able to load this on your own computer, you won't have this network lag on the graphics. Okay, so 1.9 cubic meters per second is too much. I didn't know that. Let's drop it even lesser. Go to 1.5. So this one barely accommodates the flow, and that would be how we would use this tool in a design context. So I changed the flow rate, but if we had no choice on the flow rate, what other feature could we change about our system? Let's go back to 2 and or 2.5. So let's suppose, since this is a design, hopefully this doesn't exist already, in which case what I'm about to propose might be a little hard. So I'm trying to draw a polygon around everything. And then I'm going to use group edit, and hopefully I can edit the width of the channel. Group edit, I want to go to a conduit. And let's hope that width is not a choice. Oh, we do have a shape. Go to rectangular. What we'll do now is we'll carve the channel out. We'll make it 2 meters wide. We'll stick with the 2.2 meters deep. Press the OK. Exit the editor. And now we have just increased the channel width. And I'm kind of thinking that should have an impact. So I'll rerun my simulation. Press the okie dokie. Bring back my profile. And now the flow is nicely maintained in the channel. Let's see if it's it looks like it's the correct depth of 2.2 meters, and there we've just done engineering design and concluded that to carry that particular flow rate under those conditions, we need a channel that's twice as wide as we initially specified. So our next example is a flow in a sewer. So this is very much the same thing. The only difference is the geometry. So 3 mile long, 60 inch, 50 miller genuine drafts, 1% slope. We'll specify the outfall as normal depth, and we want to see what the sewer looks like. Our design question is, can a 60-inch sewer actually accommodate that flow? And so to do that, we would build a similar model. I'm going to cheat and open the model from this morning. So it has all these features for it right now. The only thing I don't know is if we're actually at the full 50 MGDs. So we'll run it at 45 and take a look, and then we'll put it up to 50, and you'll see why there's a 45 there. So everything's essentially built the same way. We specify the outfall, we go to project defaults, set the appropriate defaults for our project. In this case, they're circular and so forth. And then lay out the nodes, and then connect the nodes with links, set the options, set the outfall conditions. Here the outfall is normal. And what normal means is it's going to use the slope of the conduit upstream of it and compute the normal depth for the supplied flow rate in that conduit and then apply it at the outfall. And I wonder if I have a profile already built. I don't. So we'll use the profile drawer. Start at node 8, end at node 1. Wonder why it labels them like that. That's bizarre. Oh, there must be a hidden node here. There we go. So there's our sewer system, and as before, we need to get out to a steady state condition. So we'll run it to the end of time, and that is what the water surface profile looks like at 45 million gallons per day. And now we'll ask the question, what happens if we go to 50? We might actually even be able to see it if I can get to the right thing. There we go. So if we change the input from 45 to 50, so I've made the change. I've not run the new simulation yet. I'm going to go look at the old report, and I want to look at a particular part of the old report right here. So at 45 million gallons per day, that line came up as zeros. So all the flow was contained in our drainage network as we anticipated. We run it again, choose OK, pull up our report again. Scroll down to the portion where it shows flooding loss, and now we have flooding loss of 0.6 million gallons is lost in the 6-hour period to flooding. And if we want to look at the diagram, we can see that here. The indication that there's something amiss is that the water is going all the way up to the top everywhere, and that's usually telling us that there's something funny about our design, and we would use that information to modify the design. I didn't want to do that. So that is our second example. So now we're going to go to the Goodwin Street sewer system. So we're just going to use this image and load that as a base map, and then we will start to identify the individual drainage areas and slowly build up our drainage network in SWMM so that we can test the hydraulics. So let's go ahead and first get the base map. I want to make a new project. Okay, so I have room for a new project. Now I have to do the part that always causes my system to crash. So I'm trying to get a connection to the website which has the drawing in it. And it takes a little bit of time because we're wearing the internet out right now. We don't need to go to CentOS, we need to go to that one. Oh, that's the wrong Atomic Kitty. We'll try that again. This one. I was trying to skip a step. It burnt me as it usually does. So we go to teaching, and this class is water system design. We get to this through Blackboard also. And we want to go to lesson 18, I think. Data links. Supplemental. I want to download the BMP. Looks like it's coming through, so maybe it's... No, it's not yet. So we will, apparently the computer is going to take 8 minutes to do something that normally takes a fraction of a second. And that's just the modern network, because seems like everything's been going slower lately. So while we're waiting for it to get here, let's go take a look at the Goodwin Street storm sewer. Oh, I didn't even leave the spreadsheet. Try that again. We're going to need that. There's no point in loading it to the SWMM server because it doesn't have any ability to read an Excel sheet. So we'll load it to this thing, and I'll have to do manual data entry. But I'm going to have to do a lot of that anyway. Okay, so we have what we did last time here. We will need to take advantage of all that. Looks like we almost had the picture here. Let's go back there, and we have only a mere 8 minutes to go. Oh, we're getting a burst of speed. So this remote desktop is hosted at a company called justhost.com. They're about, let's see, 800 versus 8. They're about 10 times as expensive as Amazon Web Services to do the same thing, and they're at least 10 times slower. So they're going to be kind of surprised when they try to renew my contract and the credit card doesn't work anymore. And we'll just transfer everything over to there. So welcome to cloud computing. It's just like things that are free. You just start switching a lot. Unless you have everything on your own computer, then there's no need to switch. So I really don't like to wait on things downloading, but we're kind of stuck. So 4 minutes, I could sing you all a song, but then everybody would log off. I could play a song on my phone, but that would even affect the download further, because this is actually partly my fault. This particular file is located on the server that's duct taped to the back of my television out in the living room. And so that server is a Raspberry Pi with a 4 terabyte hard drive strapped to it that serves 2 roles. Serves up these files like this, and I use it to watch TV from foreign countries through a VPN through my TV. It's kind of actually stupid, but it's a total of about $100 of hardware and several days of building the software to do it. So a couple minutes left. So what we'll do is I'm going to load the base map into SWMM. And then the first thing I'll do is I will establish the outfall. And then I'm going to lay these nodes out. And initially I'm just going to lay them out as dots. And then I'll go ahead and put in the node identification numbers to be consistent with the example in the Goodwin storm sewer design. Then we'll add the links, And all we'll do is we'll just use circular conduits. We're going to have to manually set the lengths anyway, and the diameters anyway, based on our design. Then we'll add drainage areas, and that'll probably take us to all that we'll get through today, and then we'll pick up the problem again next week, because I haven't described the hydrology part yet, but it will be productive to have the network laid out and ready to go for that. On your exercises / semester design project, because the exercises are all kind of put together to help make that design thing easy to put the pieces together. We'll be doing the same thing for the Somewhere USA subdivision. The only difference with that is it's laid out horizontally instead of vertically, and you're draining in the Somewhere USA to that right corner. Wow, it's using NFL time. So we just passed the 2-minute warning, so it'll be another 25 minutes before the data gets here. I could technically start drawing the network. Actually, I guess I could. We could start drawing the network now when we get the base map loaded in and then rearrange everything. That may come in handy. It may be a mistake on my part. So let me get the picture over here. See if I can get the swim interface to come up. And we have an outfall node up here. And then 1, 2, 3, 4, 5, 6, 7 nodes going down. And we'll adjust them when we get a base map. So 1, 2, 3, 4, 5, 6, 7, and we have 1, 2, 3, 4, 5 starting from here. So 7. We're going to rename them anyway. So 1, 2, 3, 4, 5, and to the right we have 2. Get them connected to the right place. So we have 1 coming here, skip, and then 1 coming here. Just put the nodes wherever it damn well pleases. See if our download's here yet. Almost 18 seconds. Oh, we're going to take an internet timeout. 9 seconds. 7, 6, 5, 4, 3, 2, 1. Then it's got to exchange checksums. All right. It claims that everything is here. So let's. I didn't want to do that. I really just wanted to switch. So let's go ahead and kill that last junction, which I don't think I want. View, backdrop. Now this is going to be kind of fun because I have to find it. Sweet. Okay, so the backdrop is loaded. And now we will move the nodes to their correct positions. I seem to think that we put a so frankly it's usually easier to put the backdrop in first than what I'm doing right now, but I didn't want to completely sit there and twiddle my thumbs while the computer downloaded software. And a lot of the apparent inability to place things is actually a network lag. Where was this guy supposed to go? I guess it's supposed to go up there. There we go. So in about 5 minutes we will end today's lesson. So I think the best we're going to get today is to get the network structure laid out, but we won't be able to get the names right, or the elevations put in. We'll do that next class meeting. So that looks like, let's see, view. There was the deal I was looking for. Oh, don't do that to me every time. Let me go ahead and save this file now so that we don't have to go looking for the backdrop every time. So we'll call this Goodwin 1. And you should go ahead and use file names as a way to keep track of incremental changes, and then you would put the final one in a production run file. So we've got the nodes laid out. The next thing would be to join the pipes, and let's go ahead and we'll just take whatever the defaults are, and we'll go take a look at one pipe. So we don't want rectangular open, so let me go ahead and change that. We want circles, so we'll choose the circle. 10-foot diameter pipe's a little bit big. As I recall, the biggest we had was 3.5, so I'll just go ahead and put a 4, and we'll go back and we manually change those pipe by pipe when we get to that. And these are going to be nice, high quality, freshly smooth pipe from Pipes R Us. And so we'll use that. This one I think still retains its rectangularness, so we have to manually change. Actually, we don't have to do that. We will delete it and then redraw it. So now we'll go ahead and just draw in the pipes. And that looks about correct based on the base map. So we'll load it back in. And even though we saved it, it still forces us to find it. And so that's where we're set up. The next thing we'll do is we're going to create drainage areas. I'm going to do one of them and show you how we'll do that. So we can draw these directly on the drawing like that, and all that is a drawing. It's not doing any sort of area calculation, and it stores it as a shaded area, and then we will have to manually assign the acreage and a few other features to get water to leave that drainage area and enter. In this case, we're going to send it to that first node, which is node 1, 1. So we'll go ahead and we'll set just that up, and then we'll be done for the day. So the node, this name is node 1-1. I'd use a decimal point, but I don't think it'll work with that. Call it the upstream node. No inflows, no treatment. For the time being, we have no other information. We don't even know its invert elevation, although 732.3, if we put it 6 feet underground, that would be 726. So that node is specified, and now this drainage area is where we tell it to drain to node 1-1. So when we're integrating the hydrology and the hydraulics, there's a little bit of requirement on our part to come up with a naming convention that's easy for us to follow. We do that, and the way we know it's attached is I'm going to zoom in. This little dashed line right there is a graphical indicator saying that this drainage area drains to that node. And that's how we're going to construct the rest of the Goodwin Street model. So let me zoom back out. I will reload the backdrop, and I want to save everything. And that will conclude today's lesson. So what we'll do next lesson is we will complete the Goodwin Street model, and then we will apply some rainfall runoff principles to it. And our goal ultimately is going to be to generate those hydraulic profiles and convince ourselves that the water that we are draining is staying in our system and not flooding on the streets. So let me go ahead and set up ending the class for today. So I will close that, disconnect, close, close that, return to Blackboard, and I think I can stop screen sharing. Let me go. I probably did say Miller Genuine Draft. I meant millions of gallons per day. I've had that MGD beaten into my head a lot of times on television, so I blame society. It's not me. It's society's fault. I hope you all found that funny. That was supposed to be humorous. We are done, so I'm going to stop the sharing, and if there's any questions, now's a good time to ask them. If not, have a good weekend. It's supposed to be nice this weekend and then start to get cold Sunday. So this is probably our last weekend of end of summer, beginning of fall. So I hope you have an opportunity to enjoy that. With that, goodbye everybody, and have a great weekend.